This video is about signal flow on edges of triangular neighborhood networks. A signal at the given level is a logical object, but we saw in a previous video that an edge itself can be represented by a pipe that has triangular neighborhood structure. At this level, a signal is a toroidal hole embedded in the pipe, or it can be a torus external to the pipe like this. So I wanted to show this in plastic models. This is a banded pipe of circumference 8 with a short toroidal hole in it. When you look at the thing endwise, you can see that the toroidal hole here is very short, and that one side is one triangular face and the other is another triangular face, but in the opposite direction. The result is that the toroidal hole is displaced slightly in the pipe. If the pipe were larger, 12 circumference for example, and instead of just 2 bands we had 3 bands where both triangular faces were oriented in the same direction, then the object would be in the center. So here I asked myself the question, could I put a similar short toroidal hole into a vertical pipe? And the answer clearly is yes. And once again, because the faces are in opposite directions, then once again the pipe, the toroidal hole is slightly displaced in the pipe. Again, we could increase the circumference of the pipe and increase the length, in which case the toroidal hole would be symmetrically located. But the main thing is here that it's clear now that short, in this case toroidal holes, can be put into either banded pipes or vertical pipes, and that if the hole is short and the faces are opposite to each other, then a displacement occurs, but if the pipe is larger and the toroidal hole is longer, then the symmetry is once again obtained. This is a model that I built in an attempt to understand how a toroidal hole emerges from a pipe. What I built here is a toroidal hole with one face, one end in the pipe, and then I've added a ball-like structure so that the other end of the toroidal hole is embedded in the object. In order to do this, these two triangular faces are slightly skewed to each other, and I couldn't use in this case 12 circumference banded pipe of pitch 0, but I had to change from a 0 pitch pipe to a twisted pipe, and so you see the pipe is twisted like this, and when you look at it like this, you can see the end-to-end structure of the toroidal hole in this side in the pipe, and then in the other side of the toroidal hole in the object. But when I tried to add structure to this twisted pipe on either end, I just couldn't do that. I mean, the symmetries were just all wrong, and so somehow this is a very dynamic state of structure with this twisting of the pipe, and as part of perhaps the emergence of the toroidal hole from being completely in the pipe to being one end in the pipe and the other end in the object. So this is a more complete model of what I imagine may happen as a toroidal hole moves from being embedded in the pipe to being a freestanding object. Motion of a toroidal hole along a pipe is something that I've not been able to simulate or have not simulated yet. So this is all just trying to imagine what the transient structures might be. The previous section just showed the twisted nature of when you have one end embedded in the pipe and the other when you have it embedded in an object. So in this model here, what I've done is I've symmetrized by building two objects external to the pipe with a toroidal hole going between both of them. In this case, the relative twists line up, and so we can build a stable structure here. And then eventually one would imagine that the toroidal hole would emerge from the pipe itself, where the object would then be bonded to the pipe. So my sense is that moving toroidal hole in a pipe is a complex and difficult thing. Certainly, making that toroidal hole emerge as an isolated object is even more complex. But my sense is that once you have the toroidal hole isolated from the pipe, then moving this toroidal hole along the surface will be much easier, because you don't have to be concerned at all with the toroidal structure here. Remember, the toroidal structure is a collection of 12, curvature 12, positive curvature 12. In this case, it's 6 8-edge nodes that make a complete curvature of plus 12. So having the minus 12 of the object and the plus 12 of the toroidal hole be isolated and stable, and then only being concerned with the motion at the base here of this three pipe as it moves along the surface, that to me seems like a simpler behavior on the part of the triangular neighborhood networks. So this is the first of the signal flow diagrams. This is a 3-edge node with one signal. The question is, where does that signal go? Does it go to the left or does it go to the right? And the only reasonable solution for this particular problem is to say, with half probability it goes to the left, and with half probability it goes to the right. A similar situation obtains with the two signals on a 3-edge node. Where do those signals go? Does one go here? Does one go back? And so with half probability you say that in this case the signal returns and this signal goes down like this. And then with half probability you say that this signal on the right returns and the other one goes forward. So each of these two cases, I mean, there's the zero case where there are no signals, and then there's always the case with all signals on every edge, and those are always constant. So for each of these number of signals and different configurations, there's always a rotational equivalent, and that's how you build up the table. So this table for 3-edge nodes would have 2 to the 3 rules, and these cases that I've just shown you are the sample cases, and then there'll be rotational equivalents of those. The 4-edge node has the same sort of thing but different symmetries. Here with one signal approaching the node, in this case here, you can say with a strong probability the signal will simply go straight ahead. But one also has to include the possibility that the signal will for some reason or other turn to the left or turn to the right. And so in order to balance off in the simulations that I've done so far, these effects, I've given this a 6/8 or 3/4 probability to go straight ahead, with a slight 1/8 probability to go to the left, and a slight probability to go to the right. You could change these numbers to 16ths or 30 seconds, in order to reduce the probability of deviating from going straight forward, but that seems to be the case. The same way, we can consider for the 4-edge node 2 signals approaching and 2 signals leaving. Always there has to be a conservation of signals entering and signals leaving, because at the second level of structure, these would be toroidal holes, and you can't change the number of toroidal holes in the triangular neighborhood syntax system when you are dealing with recursive behavior in terms of level. So in this case, the solution for the 4 is quite simple, and similarly for 2 signals in this particular configuration, the solution is unique. So this completes the 4 edge nodes. 5 edge nodes have a more complex behavior because of the symmetry. Here we have one signal approaching the node, and the question is, does the signal go to the left or to the right? So in this case, with half probability, we assign it going to the left and going to the right. One could, of course, include minor probabilities for going left like this, or right like this, or even returning. In this case, I've not chosen that, but I have a table making program, and so changing the configurations and the rules is relatively simple, and that could be an experimental issue when one's doing simulations. Here in the case of the 5, we have 2 signals adjacent to each other, and the solution is one could choose them to go in a situation where they're both adjacent to each other, where there's an adjacency like this, and then split apart like this. So these are the 3. Each case is rule is applied with a 1/3 probability. In the case of this configuration for the 5-edge node, 2 signals are separated from each other, but then using a symmetry argument, you could say that they would have to go to these 2 nodes, 2 edges. The same way, for this particular configuration of 3 signals, there's only one solution to this, and that is that one of the signals returns and the other 2 go left and right. This configuration of 5 edge node with 3 signals like this, once again, has only one solution. But when you have 4 signals, you have to choose where the signal will not go. And so in this case, there are 2 solutions with each a probability of 1/2. The 6 edge nodes are configured like this. In this case, where there's just one signal, the signal most probably will simply go forward. What I found in the simulation was that since the 6 edge nodes are the ground state, and there are so many more of the 6 edge nodes than anything else, if you make this rule be such that the signal always goes straight forward, then with low density signals in the total model, essentially nothing happens, because signals just go through nodes and there's nobody else there, and so this is the sparse case. So what I found was interesting was I would give 3/4 probability to going straight ahead, 1/8 probability to going left, and 1/8 going right. One could, of course, change this to 16ths or 30 seconds to reduce the effect of this change in direction. but I've used the 1/8 in this particular case. When there are two signals like this adjacent to each other, then they simply pass through each other, or can be considered to interact. I mean, one could consider that this thing goes like this and this signal goes like that, but the effect is the same as if they just went through each other. That's the way the symmetry works. In the case here, where they're opposite to each other, they could go either in this direction or in that direction. So you assign half probability to each of those outcomes. The case where the 6-edge nodes are in this spaced by 1, again you give 3/4 probability to this and 1/8 probability to either left or right solutions. For the 7-edge nodes, we have this sort of situation where with one signal approaching the node, the most obvious pair of solutions is to go slightly left and slightly right, each with a half probability. When on a 7-edge node, when the signals are in this configuration, you do this again with a half probability. When they're in this configuration here, there's only one solution, and when they're like this, you go for this solution. Now, for the 7-edge node, there are many other configurations of signals, and I could detail these. But what I've done is I've made, as I said, a table-making program, and the table-making program considers all of these cases. For the 7-edge node, there are 2 to the 7th, 128 cases, and many of them are rotational variants, but still there are any number of configurations of 3, 4, 5, 6 edge node signals coming into the 7-edge node, and these all have to be dealt with in some systematic fashion, and the table making program does exactly that. We've just considered the cases for 3, 4, 5, 6, and 7-edge nodes where the signal is logical, corresponding in the second level structure to one toroidal hole. We've also shown how that hole can be either bound to the pipe or in an isolated object. In any case, there's only one toroidal hole. Now let's consider the notion that there could be more than one toroidal hole, whether it too is bound in the pipe or whether it's in an isolated object is a matter of existence. Here we show a diagram for a 5-edge node where there's one signal and it has a value of 2, meaning that in the isolated object there would be 2 toroidal holes. When that object approaches a 5-edge node, we want to consider the question, what happens? And so it seems that there'd be 3 cases. With 2/5 probability, the object would remain together and would traject to the left, and with 2/5 probability it could traject to the right. But let's say that there's a chance that this object will split up when it encounters this node because of the symmetry of the node, and in which case there would be an object with one toroidal hole, or an object with going in one direction, or an object with a single toroidal hole going in the other direction. Whether these are fifths or some higher multiple which reduces the probability of this fission event is a matter of experimentation. So when we have two signals approaching the node, in this case two signal with 2 toroidal holes and one signal with 1 toroidal hole, we can assign a probability of staying of the two toroidal hole objects staying together, and these objects simply billiard ball interacting with each other, assigning a probability of 3/4 to that, and perhaps having the object split into the two-holed object splitting into two single toruses, and then the other torus just deflecting. We could give that a probability of 1/4. Although the probability values, can be anything we want to assign, as long as both cases are treated appropriately. Here's a case where, again, there's a signal with two toroidal holes and a signal with one toroidal hole. Do they simply billiard ball interact, or does fission occur? So for every case that we dealt with for each of the nodes earlier, we can deal with any of the signals having more than one toroidal hole as its composition. One would have to make a table making program that dealt with these sorts of events, but that could be done, and there could be signals for any number of toruses that would be dealt with by such a program.